So in the previous implementation, the pipeline, it was actually the first multi-threaded implementation I did. This is, the performance was horrible. And the reason for that, as we showed before, is that when you control all the concurrency and contention at such a fine grained level, what happens is you pay a huge price. You stay most of the time just looking for flags and worse. I mean, you could sleep, and if you wanted in that wait function, that would make things even worse. So if you, the idea is this exemplifies actually what a big rule that you can't be doing multi-thread in such a fine grain fashion. What you have to do is to compute things in big chunks and then synchronize. So the synchronization points have to be far apart. You can't have them so close. This domain divide implementation is an attempt to do exactly that. Let me just do the screen capture. Let's scroll capture this thing, this one. This is actually a simpler version than the pipeline. Okay. So what we do, this is the same, just that here I'm computing 2 million. This is 2 to the power of 2 million. And I think it computes that pretty fast. I mean, in a matter of less than a minute. And this number of threads. So I'm computing 2 to the power 2 million using 4 threads. Again, the same entry point, and we create we create a vector of threads as before, and we join them in the end, and here we create each empty threads. Now in this approach we are not doing pipeline anymore. What's happening here, and there is no calc, there is this structure, it's called sync, and what we do is, let's say that we want to compute 2 to the power of 100, and we have 4 threads. So what we do is we have 4 blocks, one for each thread, and each block with 25. It's not called blocks. This is actually 25 blocks. So it's more of a slab with 25 blocks. So each thread now it's confined into its own region. So it has freedom to modify what's inside without any need for synchronization. And actually this is much better because each CPU has this region of the memory in cache, so there is no cache messing up or cache migration from one CPU to the other, and that affects performance a lot. So each CPU stays confined in its own memory region, which is perfect. And in between, when the only thing we need to do is when thread number 1 goes computing and reaches the last point, it has to pass the carry to the next thread. And for that, we have this the sync struct, and that contains the number of bit that it's currently multiplying, the actual carry, and the counter. We could choose any sort of mutex, any lock in this case, but the counter is a much better mechanism, and this is an odd even counter, or odd even mechanism that we use to synchronize between the two. The way it works is, so basically that's I'm not going to explain the code. It's this is pretty much the same as the serial version. It's a copy and paste from the serial version. It's only that in the end it does that synchronization, and in the beginning also it synchronizes. So that's what this code is doing. But what I want to show is the counter. How do you actually do this? So let's suppose that you have just two threads, thread number 1 and number 2. So thread number 2, this is initially 0. Thread number 1 has 1, and it's supposed to compute 1 times 2 to the power of 19. And then initially the result is going to be a big number and a 0 carry, so nothing happens. But in the next calculation, there will be a carry going over to thread 2. And when that happens, and this is way down here, when that happens, what thread number 1 is doing, there is this counter between the two. The struct is for the synchronization between thread number 1 and 2. So the counter is initially 0. Thread number 2 will be looking at this counter and waiting for it to change. So while the counter is 0, it does nothing. When thread number 1 finishes computing the carry, let's call it CT counter. When thread number 1 finishes and has a carry, it looks at the counter. The counter is even. When the counter is even, thread number 1 can access the structure. So that's what it does. It stores the new carry here. So there is a value there, and has the number of bits. Let's say it's multiplying by 19 right now. As this number goes down, eventually this number can be like 5 or whatever is left, the number of bits. So it's not always 19. That's why we pass. So the counter is 0, so thread number 1 can change. Thread number 2 is waiting for this number to change. Once this thread finishes updating the carry and the number of bits, it increments atomically the counter. So the counter becomes 1. Thread number 2 knows when this counter becomes an odd number that it can access the rest of the structure. So what it does, it reads the carry and the number of bits into its own memory and increments again the counter becomes 2 in such a way that if for any reason thread number 1 updates and goes fast around and tries to update again and sees, for example, 1, it has to wait. So while this counter is not an even number, thread number 1 is going to wait because it knows that thread number 2 has not finished reading the old values in there. So the rule is the thread that's behind waits for the counter to be even, and the thread that's beyond the is in front of the previous thread will wait for this number to become an odd number. That's why I call this an odd even synchronization mechanism. And this is a lock free, so it doesn't access any. It's an atomic mechanism. It doesn't, at least in Intel, it doesn't access any kernel features or resources, and it's pretty much free. And if you have blocks of a good size, this synchronization mechanism will pretty much never cause contention or any other problem. It's important though that you keep the number of threads coherent or consistent with the number of blocks that you're computing. That's why in some part of the code I keep a minimum slice of 4, which is pretty small, but we should, I would recommend at least 16. So if you are computing, I don't know exactly what the point is, what the break-even point is, but I think with small blocks you end up doing so much synchronization using that sync structure that it just it doesn't compensate. It's just slower. So this number 4 is definitely small. We should have it 16 or 32 or something higher than that. And that's it. I mean, that's how the domain division works. In the end, the threads quit, and we compute the number of blocks used, and and that's printed.